Hi everyone. In this lesson, I'm going to present a few examples of the application of Eshelby's approach. Some of such applications are already published in peer-reviewed journals. Some are in PhD theses. My intention here is to give you an idea on the diversity of problems that can be solved by using the Eshelby's approach, rather than to present the detailed results of any application in particular. First, let me briefly summarize the results of Eshelby's. For an inhomogeneity, or more generally, a rheologically distinct element embedded in a uniform matrix, if the rheology of the embedding medium is linear, either linearly elastic or linearly viscous, the partitioned fields are related to the far fields by this set of partitioning equations. Lowercase symbols here represent the partitioned fields, partitioned stress, strain or strain rate, vorticity. And uppercase corresponding symbols represent far field quantities, strain or strain rate, vorticity, and stress. A and B are strain or strain rate partitioning and stress partitioning tensors, and pi and S are Eshelby tensors. If we plug in stress-strain relationship, the Hooke's law, or stress-strain rate relationship for linearly viscous materials, this set of partitioning equations then can be reformulated into this set of interaction equations. The stress difference is related to the strain or strain rate difference by this equation, and the vorticity difference is also related to the strain rate difference by this second equation. And these two equations are sometimes expressed in this form. Stress with a tilde on it represents stress difference. Stress difference is related to strain or strain rate difference, and the vorticity difference is also related to the strain rate difference. So the interaction equations defines the mechanical interaction between an RDE and the embedding medium. For simple reference, we shall call the fields, the partition fields, in an RDE microscale fields, whereas the far field fields are called macroscale fields. And the interaction equations relate the two fields by strain and stress partitioning tensors. The application of the partitioning equations are numerous, and a few examples are presented below. First, the partitioning equations allow us to track the rotation and the strain of a deformable ellipsoid. The rotation is defined by this differential equation, which is the same form as the one for the rotation of rigid objects in viscous flows. The shape change is described by this equation. A is a vector representing the three axial lengths of an ellipsoid. These two equations are coupled. Because we know the strain rate and the vorticity expressions from the partitioning equations, the angular velocity for the object can be obtained. The angular velocity is equal to the partitioned vorticity subtract a term that is called shear spin. The shear spin term is related to the instantaneous shape of the object and the shear strain rate as expressed in this expression. The details of this is presented in the lecture notes. This set of differential equation can be written in this way for an increment of deformation. If we choose an increment time step, delta t, then a one-time step update of the shape and orientation of the object can be expressed by these two equations. This numerical algorithm has been implemented in Mathcad and MATLAB. Here is a link to a Mathcad worksheet for the numerical calculation of the motion of a deformable ellipsoid in viscous flows. Details of these are presented in the lecture notes and also a set of papers of mine. Beerby et al. 1975 was the first paper in the geology literature on deformable ellipsoids in viscous flows, and Freeman 1987 was the first numerical solution of the equations. Second, the partitioning equations have been used to investigate the formation of L-tectonites in isolated rock volumes. L-tectonites are deformed rocks with a strong lineation but a weak or no foliation. They mostly suggest prolate type or constrictional strengths. Almost all L-tectonites so far reported are developed in isolated, often mechanically stronger rock units. An excellent example is from the northern Chadam in China. There, L-tectonites are observed only in granitoid rocks, embedded in a schistose rock called Tabandakan complex. Constrictional strengths associated with rheologically strong units are most easily investigated using the partitioning equations. Partition fields in the RDEs rather than the macroscale fields are then used for the development of L-tectonites in the RDEs. For a long time, a popular interpretation of L-tectonites has been the homogeneous transtension model of Sanderson-Marchini. However, this model predicts constrictional strength field throughout the deformation zone, which has never been reported in nature. L-tectonites formed by partitioner fields mean that they can occur in any deformation environment. Oblique divergence boundary conditions in nature likely produce shallowly dipping shear zones in the ductile lithosphere rather than homogeneous transtension. Isolated L-tectonites can develop in rheologically strong rock units due to partition flow. Third, the partitioning equations have been used to model the development of quartz CPOs due to partition flows. Keelam et al. Presented these quartz CPO data from a single large thin section of amazonite. Quartz porphyroclasts are present in a monolithic matrix of mica, feldspar, and dynamically crystallized quartz. The shape fabric presented by the deformed quartz porphyroclasts and the deflection of the foliation clearly indicate a dextral sense of shear and a strength gradient as indicated by this green arrow. The quartz CPOs are quite variable from one porphyroclast to another. They appear to be of opposite sense of shear. As these CPOs are from individual quartz porphyroclasts, clearly each quartz porphyroclast is a unique rheologically distinct element. The CPOs have developed due to partition flows in these individual quartz RDEs rather than due to the shear zone scale flow. When partition flows are considered, Bandari and Jiang was able to reproduce the spatial variation of the quartz CPOs. There is a strand-induced with vorticity rotation of the CPOs. At the lower strand stage, the quartz CPOs are like these yellow-colored patterns. As strand increases, they are rotated slightly, and the peripheral C-axis maximum is parallel to the shear zone normal. And as the strand further increases, they tend to rotate past their shear zone normal. Key point here is to use the partition flow rather than the shear zone scale flow. Eshelby's solutions also applies to the deformation in the medium, in the vicinity of their RDE, and that is called exterior point solutions. The partition field in the rheologically distinct element is called the interior field solution. The interior field and exterior field solutions together have been applied to the formation of flanking structures. Flanking structures are an association of features made of a cutting element, CE here, and an external host element, HE. The cutting element is predeformational. Its presence caused the heterogeneous deformation in its vicinity. Foliation or any marker deflections in the vicinity of CE gives rise to flanking structures. Flanking structures dies out when the cutting element terminates. Cutting element can be a fault, a shear band, or a vein. Clearly, the flanking structures are related to deformation in the vicinity of the cutting element. We can regard the cutting element as an attribute in homogeneity. The exterior field solution gives the strand and vorticity field in the vicinity of this cutting element, and hence they can be used to investigate the development of these flanking structures. Depending on the relative rheology, the initial geometry, and the imposed macroscale flow, different flanking structure geometries can be developed. Some of them are S-type with a synthetic offset, others called N-type, and still others having this anti-aesthetic offset. Detailed investigation of this is in a PhD thesis, Ankit Bhandari. Finally, the partitioning equations and the Eshelby's equivalent inclusion approach provide an elegant means to investigate the mechanical interaction between a confined ductile shear zone and the country rock. This is a typical Ramsey-type shear zone confined in an undeformed gabbro. Confined is the key word here. Traditionally, this type of zones are treated as infinitely extending zones between parallel walls. In kinematic models, such as those presented by Ramsey, the interaction between the country rock and the zone itself is through an imposed zone parallel displacement. In mechanical models, it is also assumed that these zones extend forever. And the consequence of that assumption is that the shear stress is constant throughout the zone and in the country rock. In reality, these zones do not extend very far. They are confined within country rock. They are better represented by a flat RDE, such as a penny-shaped RDE, confined within the country rock. If we assume that both the country rock and the shear zone rock are viscous materials, then we can directly use these interaction equations. The country rock has a much higher effective viscosity so that the strand is concentrated in the zone, leaving the country rock essentially undeformed. It is also possible to regard the country rock as being elastic and the shear zone viscous. So the interaction between the country rock and the shear zone is a viscoelastic one. In this case, we can make use of Eshelby's equivalent inclusion approach. We replace the stress within the shear zone, lowercase sigma, by a viscous stress, which relates to its strain rate and viscosity. These will lead to a differential equation for the strain rate of the shear zone domain. We can even regard a crustal-scale shear zone as a pre-existing RDE subject to lithospherical scale tectonic boundary conditions and investigate the finite strand geometry in the shear zone. These lines of research are in PhD thesis of Ru and Meng at the University of Western Ontario. So to summarize, Eshelby's solutions provide a powerful means to investigate many geological problems, such as the ones I have just presented. In the next lesson, I will discuss another aspect of the application, that is homogenization. Both partitioning and homogenization are based on Eshelby's solutions. Partitioning gets microscale flows from macroscale flows, whereas homogenization gets the overall properties of the material from RDE properties. The discussion in this lesson is based on the assumption that the rheology is linear. How we deal with the nonlinear rheologies will be treated in later lessons. That's it for today. Thank you for your attention.